Hey everyone, welcome. I'm absolutely thrilled to have you here for this explainer. Today, we're diving into something pretty amazing. The very system that is keeping you alive right this second. Yep, we're talking about body fluids and circulation. We're going to take a micro to macro approach for this one. That means we'll start super small, looking at the tiny microscopic elements actually floating in your blood, and then gradually zoom out. We'll check out the magnificent pumping engine that is your heart, and finally, look at the massive highway system of vessels delivering oxygen to literally every cell in your body. It's a brilliant piece of biological engineering, so let's just get right into it.
Okay, let's dive into this. Here is our roadmap. First, blood and lymphatic fluids. Second, the anatomy of the heart. Third, the cardiac cycle. Fourth, reading the ECG. Fifth, pathways of double circulation. And finally, number 6, circulatory system disorders.
Section 1. Blood and lymphatic fluids.
Now, what's really interesting here is that before we can even talk about the pump itself, we really need to understand the fluid it's pumping, right? This is the microscopic foundation of the whole system. Now, you might not think of it this way, but blood is actually a specialized connective tissue. About 55% of it is plasma. Think of plasma as the watery transit system. It's this straw-colored kind of viscous fluid that's mostly water, but it carries absolutely crucial proteins, minerals, and nutrients. The other 45%? Those are the formed elements. These are the cells doing the real heavy lifting for us. You've got your erythrocytes, or red blood cells, carrying the oxygen, your leukocytes, the white blood cells fighting off infections, and the platelets, which literally rush in to clot your blood the second you get a cut.
So, quick question for you. Are you a universal donor? To the naked eye, all human blood looks exactly the same, but chemically, it's a whole different story. It all comes down to the surface antigens on our red blood cells, specifically antigens A and B. This gives us our ABO blood grouping. If your blood happens to lack both A and B antigens, you're in Group O. And because Group O doesn't have these antigens to trigger an immune response in someone else, Group O folks can donate to literally anyone. They are the universal donors. On the flip side, if you're Group AB, your blood naturally lacks antibodies against A and B. That makes you a universal recipient, meaning you can safely accept blood from any group.
But wait, beyond the ABO system, there's another absolutely critical factor, the Rh antigen. Nearly 80% of all humans have this antigen on their red blood cells. If you have it, you're Rh positive. If you don't, you guessed it, you're Rh negative. Matching this factor is a big deal during blood transfusions, for sure, but it's also wildly important during pregnancy. Here's why. If an Rh negative mother carries an Rh positive baby, her body might actually produce antibodies against the baby's blood during delivery. If she has a second Rh positive pregnancy down the line, those antibodies can cross the placenta and destroy the fetal red blood cells. It's a severe condition called erythroblastosis fetalis. Now, thankfully, modern medicine can easily prevent this with specific antibody treatments, but man, it just goes to show how incredibly specific our body fluids really are.
Section 2. Anatomy of the heart. All right, let's zoom out from the fluid itself and look at the magnificent engine moving it all around. Your heart is roughly the size of your clenched fist, sitting right there in your thoracic cavity. It's a marvel of anatomy that brilliantly features 4 distinct chambers. Up at the top, you've got 2 relatively small, thinner-walled atria. Right below them are the 2 larger, thicker-walled ventricles. Why the thicker walls? Well, those ventricles have to forcibly pump blood out over much longer distances. And situated right between these chambers are one-way valves, like the tricuspid and bicuspid valves. These are game changers because they ensure the blood only ever flows in one single direction. They completely prevent any dangerous backward flow. But what actually tells this muscle to pump? Well, the heart has its very own internal electrical system. Up in the right upper corner of the right atrium, there's a highly specialized patch of tissue called the sinoatrial node, or the SA node. This is your body's natural pacemaker. It's auto-excitable. That means it literally generates its own electrical action potentials without needing any outside signal from the brain. It fires off about 70 to 75 action potentials every single minute, essentially sparking the rhythmic pumping action of your entire heart.
Section 3. The cardiac cycle.
Okay, let's actually slow our pace down here for just a second. We really want to map out the complex sequence of events that happens in the literal fraction of a second it takes for a single heartbeat. The cardiac cycle is essentially a 1-2-3 rhythm. First up is joint diastole. All 4 chambers are totally relaxed and blood is just passively flowing down into the ventricles. Second, that SA node fires, causing atrial systole. Both atria contract at the exact same time, pushing the last bit of blood into the ventricles. Third, the electrical signal travels down, triggering ventricular systole. Those massive ventricles contract, the internal valves aggressively snap shut, which gives us that classic lub sound, and blood is violently forced out into the arteries. When the ventricles relax, the exit valves snap shut to stop backflow, giving us the dub sound. Lub, dub, lub, dub. This whole sequence takes just 0.8 seconds and repeats roughly 72 times a minute. Section 4. Reading the ECG. So we know the physical pump action now, but how did doctors visualize this totally invisible electrical cycle? I mean, we've all seen medical TV shows, right? The familiar pip, pip of the hospital machine. So the crucial point here is that an electrocardiogram, an ECG, is simply a graphical trace of that exact electrical cycle we were just talking about. It's an ingenious way to visualize those invisible action potentials as they sweep through the heart muscle. When you decode the graphs and match these waves to the physical contractions, it tells you exactly what the heart is doing. Take that first small bump, the P wave. That represents the electrical excitation that makes the atria contract. Then you have that massive sharp spike, the QRS complex. That represents the depolarization of the ventricles, kicking off the powerful ventricular contraction or systole. And finally, the T wave represents the ventricles repolarizing, meaning they are returning to their normal, relaxed state. By just glancing at the shape and timing of these peaks, doctors can instantly spot if there's any abnormality in a patient's heartbeat. Section 5. Pathways of double circulation.
Let's zoom out once more and see how this all builds into a massive highway system. Once blood is pumped out of the heart, it enters this incredibly efficient double loop. You see, mammals and birds use a strict double circulation system. First, the right ventricle pumps deoxygenated blood over to the lungs to pick up fresh oxygen, and then it shoots right back to the left side of the heart. That's your pulmonary circulation. Then, the left ventricle powerfully pumps that fresh, oxygen-loaded blood out to all the tissues in your body, delivering all those vital nutrients before it returns, deoxygenated, back to the right side of the heart. That is the systemic circulation. This double loop is an absolute lifesaver because it ensures oxygen-rich and oxygen-poor blood never ever mix.
Section 6. Circulatory system disorders. Now, we've explored just how perfect this system is when it's firing on all cylinders. But we also need to look at the clinical side, what actually happens when this intricate biological machine breaks down. I'm sure you've heard these numbers before. 120 over 80 millimeters of mercury. That is the gold standard measurement for healthy blood pressure. That top number, the 120, is your systolic pressure. That's the raw force when your ventricles are actively pumping. The bottom number, the 80, well, that's your diastolic pressure, the resting pressure in your vessels between those beats. The problems start when those numbers stay consistently at or above 140 over 90. That's hypertension or high blood pressure, and over time it puts immense strain on your heart and vital organs. Then we have coronary artery disease, where the actual vessels supplying blood to the heart muscle itself become narrowed by plaque, deposits of fat and cholesterol. If the heart muscle doesn't get enough oxygen because of that blockage, you get angina, which is acute chest pain. And ultimately, all this chronic strain can lead to heart failure. That's literally the state where the heart simply isn't pumping blood effectively enough to meet the body's needs. It really goes to show how physical blockages or high pressure can completely compromise the entire circulatory mechanism. And that brings us to the end of this explainer. But before we wrap up, I want to leave you with something to really think about. We learned today that cardiac output, the volume of blood your heart pumps every single minute, averages about 5 liters in a healthy person. That's like pumping 2.5 large 2-liter soda bottles every single minute. But that output is directly tied to how efficiently your heart functions. So what does this all mean for you? Well, based on your daily habits, your diet, your exercise routine, your stress levels, how might your lifestyle be affecting your own biological pump? Take care of that engine, folks. It is quite literally the only one you've got. Thanks for joining me today, and keep learning.